Welcome. Well, today we're going to be talking about probability. The learning objective is to understand how probability quantifies uncertainty and relate the probability of an event to the likelihood of the event occurring. To understand how relative frequency can be used to estimate the probability of an event and apply this approach in practice. We're going to be looking at sample spaces, some probability rules, assigning probabilities, the product rule, and long-run relative frequency as an estimate of the probability of an event. Now, probability is the extent to which an event is likely to occur. It's measured by the ratio of favorable cases to the whole number of possible cases that could occur. The idea of probability is empirical. It's like doing experiments. It's based on observation rather than theorizing. Probability describes what happens in many trials. So we know that if you flip a coin, you could either get a head or tail. So you have a 50-50 chance of flipping and getting a head or tail, but what does that mean? That means if I keep flipping a coin over and over and over again, about half the time I'm going to see heads and half the time I'm going to see tails if the coin is fair. This is called the law of large numbers. As the number of repetitions of an experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of that outcome. Now we're going to want to talk about probability models. They're descriptions of chance behavior, and it contains two parts: the list of all outcomes, these things called outcomes, and the probability for each of these outcomes. So first we have to figure out how can we list the possible outcomes, and then how can we find the probability for each outcome. So we have to look at some definitions. First, an experiment. It's a repeatable process where the results are uncertain. Outcome, one of the specific possible results, and the sample space is what we call the set of all possible outcomes. The number of outcomes can be finite or infinite. Now, listing the sample space, generally speaking, we use a capital S. So in this example right here, when we talk about the sample space for rolling a fair die, we would write it like 1, 2, 3, 4, 5, 6. So when I roll a die, I only have 6 possible outcomes that would come out. That's my sample space. One of the outcomes would be to roll a 4. So we call that thing an outcome or a specific outcome or an event, a singular event, and it would look like this. And of course, our experiment was rolling that fair dice. So looking at this idea of an event, it's a collection of some or one possible outcome. It depends. It could be a simple event, such as rolling the 4 that we talked about, or rolling a 2, or a compound event, more than one event. So something like rolling the dice and getting an odd number, rolling the dice and getting 2 and 4, or rolling the dice and getting an even number. So we have different types of events. When we talk about events, we use capital letters. So I could use E to say rolling a 2. I could write it like that, or I could say E is, rolling an even number. But if I want to explicitly write what that means, I could do 2, 4, 6. So I could subscript these to show that I'm talking about 2 different events that could possibly happen in this situation where I roll a dice. This one would be a simple event. This one would be the compound event. We talk about different types of events, the complement of a particular event. That means if we have an event, it's everything that isn't in that event. So if I said rolling, so in the last example I said rolling a 4 or a 2, something like this, the complement of that when we roll a dice would be rolling a 1, 2, 3, 5, or 6. Everything that the event is not. When I put these two together, I get the complete sample space back. So that's going to help us talk about union. That if I had E union its complement, I would get back the sample space. So union is you take one set and you add in the other set because either E is going to occur or E prime will occur. That's what the union means, A or B or both. So if I had economists as A, B is a professor and C is woman, A union B would be all economists or all professors. If I union A, union B, union C, then that would be all economists or all professors or all women. So if I had a set, we'll call this F, is 1, 3, and 5, and G, event G, is 7 and 9, then F union G would union all of these together. So it'd be 1, 3, 5, 7, and 9. If I had A, and that was 1, 4, 6, and I had B was 3, 4, and 5, and I union these two, I would then have 1, 3, 4, 5, and 6. I wouldn't write 4 twice. I'd only write it one time. And now I've included everything in its union. The intersection, or the and statement, the intersection of A and B would mean that you see elements in A and B that were together. So in this case, we'd say A intersect B is all economists who are professors. And A intersect B intersect C is all economists who are female professors. So looking at another example would be something like if I let D be 1, 3, 5, and 7, F be 2, 4, 6, and 7. And I said, what's the intersection of D and F? What's in both D and F? Well, the only thing I see in common is 7. So that's what the intersection of D and F is. Now let's say I make another set, G, 2, 4, 6, 8, and I look at D intersect G. Well, there's nothing in common between these two sets. And how do we write that? We write it as the empty set. Another way people write the empty set is just 2 brackets. That means there's nothing in that set. And if this is true, we say that D and G are mutually exclusive. They're disjoint sets. So let's look at some very important probability rules that will help us later on. First of all, probabilities are numbers between 0 and 1. If you're talking about relative frequency, we can't have anything less than 0. There's no such thing as an event negatively happening. It doesn't make sense. Either you see it 1, 2, 3, 4, 0 times or something like that, but you don't see something -1 times. That wouldn't make sense. So probabilities have to be numbers between 0 and 1, and you can't see something more than you did it. So that's why it can't be more, because remember, it's the relative frequency of seeing something. All possible outcomes together have a probability of 1. Now, if two events have no outcomes in common, the probability that one or the other occurs is the sum of the individual probabilities. And the fourth rule is the probability that an event does not occur is 1 minus the probability that the event does occur. So let's see what those rules look like. So those are the words of it. Let's see what they look like. Probabilities of an event, we write it as the probability of event A. And we would say that that probability has to be numbers between 0 and 1, proper fractions. If S is a sample space in a probability model, then the probability of that sample space occurring equals 1. That's rule number 2. If A and B are disjoint, that is, they have no elements in common, the probability of A or B is the probability of A plus the probability of B. This is the addition rule for disjoint events. We'll later learn what happens when A and B do have elements that are in common. But if they're disjoint, this is true. The complement of any event A is the event that A does not occur, written A and you superscript it with a C, or sometimes you'll see it like this. That's a complement too. So the probability of the complement is 1 minus the probability of A, because if you remember, A union A prime or A complement was the sample space. So the sample space has to equal 1 if we take the probability. And since those are disjoint, you'd say the probability of A plus the probability of B. We just learned that in Rule 3. And we know the probability of the sample space has to equal 1. We learned it here. So that, and that's A prime. Sorry. Or A complement. And now you can make this equation. So we also know that the probability of A then would equal 1 minus the probability of A complement. I'll use the prime so you see C and the prime. Visually, what is this? If two joints are disjoint, they have nothing in common. They're literally separated from one another. But if they do have events in common, the events would be between both of them. So that's kind of what it would look like in what we call Venn diagrams. So that's why the probability of A plus the probability of B is the OR statement. We just add these elements in here with those if it's disjoint. Now probability must satisfy these rules. There are some special types of events also. If an event is impossible, then the probability of it occurring has to equal 0. If the event is certainly going to happen, the probability then would equal 1. In statistics, what we consider an unusual event is if the probability of that event is less than 5%. So things that have a probability of 5% or less are considered unusual, as a rule of thumb. Now, how do we compute probabilities? Well, in the empirical way, if we're doing an experiment, the number of trials would be on the denominator. And on the numerator is the number of times we see what it was we were looking for. That ratio of favorable cases, here's our favorable cases, the frequency of E, to the whole number of cases that would be possible, number of trials of the event. This will become a good approximation for the probability of event E if we have a large number of trials. It's that idea of the law of large numbers. So how do we do this? Let's look at an example. So we want to determine what proportion of students at a certain school have type AB blood. So we perform an experiment. That would be we take a random sample of 100 students. If out of those 100 students, 3 have AB blood, then we could use our empirical rule. The probability of having AB blood is 3 out of the 100. 3 is the favorable cases, the people that have AB blood, divided by the whole number of possible cases. Well, we only sampled 100 people. So we would say 0.03, and since 0.03 is less than 5%, it would be unusual for someone to have AB blood. That's how we use it. Now the classical method is where we absolutely know what the sample space is and we're trying to find the probabilities, the exact probabilities. Now, how we get the total number of in our sample space and an event, sometimes you have to use numerical methods to find these, so it can be complex. So we always do easy cases. That's why you see dice and decks of cards, because it's easy. We've got a sample space right in front of us. So let's look at rolling a die. We know that we can roll a 1, 2, 3, 4, 5, 6. There are 6 possible outcomes. So our sample space, the number in our sample space, this is how we write it up. The number in our sample space is 6. Now let's look at the event of rolling an even number. In that event, I could roll a 2, 4, or a 6. That means that the number in my event E is 3. So if classically I want to calculate the probability, the number of ways I get what I want is 3. okay, divided by the 6 possible outcomes. So the probability of that event is 3 out of 6. Or you could write it as 1/2, or you could write it as 0.5. You could also say 50% of the time you'll roll an even number if you did it over and over and over again. But we know if I roll a dice, I could get a 1. I could roll it again and get a 1 again. I could roll it again and get a 1 again. And you're going, whoa, where's the 50% here? Because it's in the long term. If I roll a dice many, many times, about half the time I'm going to see an even number. So what happens when we do have two events that are not mutually exclusive? What do we do? It can't be just the probability of A plus the probability of B. That would be wrong. Why? Let's look at this. Let's say that A is 1, 2, 3, and 4. And B is 4, 5, and 6. Okay? And I say I want to union these two. If I union them, I'm saying what's in A or B or what's in both. Well, A has a 1, A has a 2, and a 3. A and B both have 4, but I don't write it twice. I only write it once, and then a 5 and a 6. So the probability, so I can't count that 4 twice. So how does that deal with probability? Well, I have to, since 4 could have been counted twice, I've got to subtract that off when dealing with the probability. And let's see how this is done. So it's kind of weird when we have a problem and we're trying to find probabilities. We start with the centermost, the one that is in the intersection. So in this example, we look for what's going on from the middle and work our way out because, let's look. We know that there are 10 that are economists, professors, and women. So there are 10 that go in here. Now, if I want to know professor and women, so this is this whole intersection right here, professor and women, I know there are 30, but 10 are already accounted for. So in order to get what's just in this box right here, I would have to say 30 minus the 10, so the answer here would be 20. And I would do that for each of these intersections. And then for P, when I just want to say professors, this many of the 300 will already be taken, so I have to take 300 minus each of those separate pieces. That's when you have to take into account that there was something in the intersection. So you can finish the rest of that problem. Now the multiplication rule for independent events is very important. That the probability of A and B, if A and B are independent, is a probability of A times the probability of B. That comes in handy when we're trying to find probabilities. So in the PowerPoints, I have lots of examples for you to work through, and I highly suggest that you go through them. I show you what's called a tree diagram of the situation where you can look at the outcomes and also find probabilities, and using that product rule for finding probabilities, and looking at special cases called a pruned tree. These are all ways to help you find your sample space and an event to find probabilities. And remember, in the empirical way, it is, once again, you look at the ratio of your favorable cases divided by the whole number of cases that are possible, and that's how you find the probability. Well, thanks for watching.